All right, I believe that we are back up and running. I'm going to expand this here. Again, thank you for your patience today as we learn a little bit more about what we're capable of here. We ran into a little bit of technical difficulty with our Zoom connection today, and so we're going to try to go directly through the Facebook Live. And I believe I have full screen now, so that is great, and I'll be able to do our program today. So if you are out there with me and want to ask questions, please ask those in our chat feature. Otherwise, this will be available on our website for and our Facebook site for replay. And so if you're watching later, please do take advantage of either entering your questions in our comments or going ahead and giving me an email at scott.harris@fernbank.edu. But this is our second episode of our Fernbank Rocks series. Today we're going to talk about igneous rocks, and of course here in the image you see igneous rocks forming. You have lava coming out over the surface and cooling into an igneous rock that we call basalt. Of course, if we look at the rock cycle, we might recall there are three different major rock types, right? And I like thinking of igneous rocks as the starting point. There really isn't one, but it's kind of like 285 around Atlanta, right? If you get on the cycle, you have to get on somewhere. And so we can start talking about the formation of rocks from a liquid. See, metamorphic rocks, sedimentary rocks, we take the solids and we break them up, or we change them with heat and pressure. For igneous rocks, we start with another phase. Most of the time, you think about that as liquid magma, but as we'll find out, that's not the only type of igneous rock. All right, so to review a little bit from our first episode, just ask a question of what is a rock? And the technical definition is sort of spelled out here for you. A rock is an aggregate of minerals. That's just a group of minerals, right? And they can be just a group of the same mineral, like quartz, can be put together to form the metamorphic rock quartzite, or often as a sedimentary rock, sandstone. There's even an igneous rock that's made all of quartz. We either have vein quartz or something called a quartzolite, believe it or not. But most of the time we have a group of many different minerals, but we can also have glasses. Glasses like obsidian glass we'll talk about. You can combine minerals with glass or just have glass, and that can still be a rock. Or we can have a combination of minerals, glasses, and even broken up rock fragments. Imagine that you have a magma that chills to a glassy obsidian. It has minerals around it from magma that's cooled at different rates, and then the volcano explodes and you get rock fragments of things that were already there. And all of those get put together into a rock that we call a volcanic breccia. So rocks can be made of a number of different things there. Here are some definitions of rocks straight from the Montgomery textbook. And these are the ones that you normally hear about, but are they complete? And for today, we're just going to concentrate on those igneous rocks. So the simple definition you always hear is formed by the solidification and crystallization of cooling magma. But again, I said that's not the only thing that can cool to form an igneous rock. The point with igneous rocks is we start with something hot and we cool it down. That's true. But if we want to expand this out and get and so it encompasses all the igneous rocks that geologists deal with, a better definition is it's formed by the solidification and or crystallization. See, you have to have those glasses in there, right? You could solidify to a glass without crystals forming. So solidification and or crystallization of cooling magma, or crystallization from hot fluids like really hot water. Now, how hot? Well, typically we talk about fluids that are over about 100 degrees centigrade, 100 degrees Celsius, right? Some igneous petrologists, we go up to 300 or so. But the point is, it's hot. For if we have cool fluids, cool water running, those would form sedimentary rocks. But we're talking hot, and we're talking at least boiling hot. We can also have condensation from a vapor. That's a gas. We can have gases condense, like, when they form ice crystals. If they cool to form a solid, they can form minerals and form igneous rocks that way. One of them that you often see is around volcanoes is sulfur. Blocks of sulfur. Those are igneous rocks that are formed by condensation from a vapor. There are also some weird sort of igneous rocks out there. They're kind of transitional from igneous rocks to metamorphic rocks. They're kind of like if you take metamorphic rocks in the heat and pressure, you're squeezing them so tight that you end up kind of partially, not quite melting them, but creating this sort of taffy-like toothpaste stuff. And we call those migmatites. They typically form very, very deep inside of the Earth's lithosphere. But where do we find igneous rocks? We want to talk a little bit about that. And this is a cartoon that shows you some of those. You see a lot of the red hot magmas here. And you have different places where we create melts in different ways. Like in the middle of the ocean, we can, I'm going to get see if my laser pointer will work here. Out in the middle of the ocean, we have areas where Earth's tectonic plates are moving away from each other. There, the mantle underneath rises up and it decompresses to form some melts. We get volcanoes along mid-ocean ridges that way. There are also areas where water is being taken down on slabs of material at subduction zones. There, that water combines with the minerals in the mantle, lowering their melting temperatures and creating the opportunity to create magmas that rise up and erupt out sometimes of volcanoes. We even have areas where the crust and lithosphere in a continent is rifting apart, just like at mid-ocean ridges, and we can produce mafic basaltic magmas inside of continents that way. And we have other areas like underneath Hawaii where we have superheated areas of the mantle that rise up and decompress at their very tops and create magmas that can create those island chains. There are many different types of igneous environments out there. Now, just a few little extra definitions here that we could talk about. We talk about rocks that are aphanitic. That's the fancy term for fine-grained. We talk about those that are phaneritic. That's coarse-grained. And porphyritic. That's coarse grain inside a fine grain. We have a coarse grain ground mass, as we call it, a coarse grain phenocryst inside a fine grain ground mass or matrix. It's like having big, it's just like having big pieces of chocolate inside a cookie, right? Think of that chocolate chip cookie. You have the big chocolate chips inside of the ground mass that is the rest of the cookie. So what do those mean? And we have some other textures. You see they're glassy, vesicular, pegmatitic. What do those different things mean? Well, we have to kind of interpret those. So fine-grained igneous rocks, we interpret as cooling very fast from a magma or a gas. That means the crystals didn't have very long to grow. Phaneritic, coarse-grained rocks, well, they cool slowly. It's like when you have a lot of time, those crystals can grow bigger and bigger. And then porphyritic rocks, being a combination, they cool slow. The magma's cooling slowly underground, and then like a volcano goes off, and the rest of the magma cools fast, trapping the slow cooling part, the big phenocrysts, as we call them, inside that ground mass. Then glassy, that's where crystals can't form at all. So that's really, really fast. Vesicular simply means gas bubbles. So there's gas coming out, creating that peculiar texture that sort of looks like Swiss cheese. And then pegmatites, that's just a fancy word for really big crystals. And sometimes that means really slow cooling. Or sometimes it just means the chemistry is a little strange, that the crystals are growing in a way that really doesn't fit into everything we've talked about so far. This is an example of pegmatite where you see really big crystals. And this is a pegmatitic dike. going through a granite. So you see those different crystals of microcline and quartz and biotite micas and plagioclase in there. We're going to talk more about those. When we talk about igneous rocks and classification, we have to understand the minerals that make them up. And we generally talk about these in broad categories of mafic minerals and felsic minerals. Mafic stands for magnesium and iron rich. All of these minerals we're going to talk about are silicate minerals. They're composed mainly of silicon and oxygen, the most abundant elements in Earth's lithosphere. But other things have to go with those. So when you have a lot of iron and a lot of magnesium, they produce these mafic minerals that go into producing mafic rocks like gabbros and basalts. They're composed of calcium-rich plagioclase feldspar, pyroxene, and olivine. On the other end, felsic means feldspar, and silica-rich. Pure silica we talk about as quartz, so it's like feldspar and quartz-rich. And they're produce granites and rhyolites, and they're made of quartz and potassium feldspars like microcline and orthoclase. Sodium-rich plagioclase feldspar, and also bits of muscovite and biotite, and even a little bit of hornblende, or what we call, the broader term is amphiboles. And then there are rocks in between those, intermediate rocks, as we call them, diorites and andesites. We also want to think about where these form, because as you saw there, we have granites and rhyolites are felsic igneous rocks. But why do you have two different ones there? Well, they form in different places at different cooling rates. Granites are going to be those coarse-grained phaneritic rocks. Rhyolites are going to be those that are cooling fast coming out of the volcano. So when we talk about plutonic igneous rocks like granites, those are ones that crystallize beneath the surface. They cool beneath the surface and they become coarse-grained. I'll go ahead and fill those in for you. Volcanic rocks, on the other hand, crystallize on top of, or at least very near the surface, giving the opportunity to lose heat fast, and that produces fine-grained or aphanitic textures. We call these intrusive igneous rocks plutonic igneous rocks because they're in the underworld, like Pluto. We call the extrusive ones that come out on the surface volcanic, after Vulcan, the Roman blacksmith of the gods, or in Greek, Hephaestus. He was inside the volcano off of Italy, making the weapons for the gods. And as he made those weapons, the hot material flew out. And that's how the ancient Greeks and Romans saw that. So we have plutonic, crystallized inside or cooled inside the Earth's lithosphere. Extrusive, coming very near the surface and even out onto the surface as lava flows and pyroclastic eruptions. When we look at those different environments, we also have different names for those different plutonic and volcanic rocks. Everything from batholiths to stocks to seals to laccoliths and dikes. And then we have volcanic things at the surface. So let's look a little bit at those. Here's an example of a laccolith, kind of like a big bulb of magma that has pushed up rocks. Well, where are the rocks around it? Well, they've eroded away, right? Leaving behind this stand of crystalline igneous rock here at Devil's Tower in Wyoming. Sills are tabular bodies. They're like tables that are inside the layers of the rock. Here's an area where the sedimentary rocks have weathered away, leaving exposed seals in the Palisades along the Hudson River of New York, or in Devil's Postpile in California. Dikes are intrusions that cut across other rocks. They don't form tables within them or big bulbs. They cut across them. And here we see dikes emanating out from shiprock in New Mexico. And we see dikes that fed huge lava flows in the Columbia River of Washington and Oregon. They are, as I say, transitional from plutonic to volcanic. And so sometimes they can be quite fine-grained material. When we get to the surface, though, we have the insides of the volcano that sometimes leave behind volcanic pipes and necks. And then we have those lava flows. And lava flows come in all kinds of different varieties based on what kind of chemistry the magma had and what kind of minerals it forms. You see, the different chemistries that lead to those different minerals lead to different flow properties, or what we call viscosity. Low viscosity means it's really runny. And so here we see basaltic lavas flowing out across the surface or through lava tubes there in Hawaii. Very hot, very runny. Intermediate compositions of lava, they are stickier. They form areas like this andesitic flow coming out from a volcano called SP in northern Arizona. This is a big, sticky andesitic flow moving out with very, very high sides. And then even stickier, we find rhyolite lavas. That's the extrusive, the volcanic equivalent of granite. And they're so sticky they can't move very far, and so they form big domes like Little Glass Mountain here in the Cascades of Northern California. Very, very sticky. And sometimes then we have eruptions. Eruptions that produce things that we call ash and tephra and pumice too. If it's a really, really felsic magma composed mainly of those potassium feldspars and quartz, those can produce very, very vesicular, gas bubble rich pumices that come out of these explosive eruptions like we see here at Montserrat in the Caribbean. But again, as we classify these, we have to look at the difference between plutonic and volcanic. We've just seen those different environments. And then again, the types of minerals that they have, ranging from quartz, different feldspars, from sodium feldspars on the left to calcium feldspars on the right, and then iron and magnesium rich, what we call ferromagnesian minerals there for our basalts and gabbros. This is basically a giant Lego problem. This is the way I want you to think of it. You have different Legos, but they're only available at different temperatures. So at high temperatures, we have Legos that are called the minerals olivine and augite or pyroxene and anorthite, calcium plagioclase. Now notice that these are very iron and magnesium rich and calcium rich. They don't have a lot of silicon in them compared to the minerals we're going to see in a minute. At these very, very high temperatures, the magmas of the right composition, these have to start in the right place, like these typically start from melting of upper mantle rocks. And at these very high temperatures, we can construct olivine, augite, and anorthite. Those are our high temperature Legos. We have medium temperature Legos. Now notice that they don't have as much iron and magnesium. They have some. They don't have as much calcium. They have some. But we produce a group of minerals called plagioclase that range from calcium to sodium rich varieties. From what we call albite at one end, the sodium end member, to anorthite at the other end we already mentioned, the calcium rich end member. We have biotite, mica, and hornblende. Now also notice that the biotite and hornblende have something that we haven't seen so far. They have that OH at the end of their chemistry. That's water. That means that the water can be a part of these. So that's already telling you that the temperature is not so high. As we go to even cooler temperatures, we have alkali feldspars that are very rich in potassium and sodium. Sorry, that shouldn't have the Ka. That should just be K there for potassium. And then Na for sodium. And we have muscovite mica, the silvery white mica. And then quartz. These are the minerals we'd find in low temperatures. Now, what's the difference in temperature? All right, so those mafic minerals, those pyroxenes, the augite and olivine and anorthite feldspars, those form typically at 1100 degrees and higher, 1100 degrees Celsius. The alkali feldspars, quartz, muscovite, they typically stabilize at temperatures that are under 900 degrees. So we could think about the basalts flowing in Hawaii. They erupt at temperatures approaching 1200 degrees Celsius. Granites forming inside of a magma chamber typically are around 800 degrees Celsius. Still very hot to our touch, but much cooler than those basalts. And so if we play our game of Legos, we can compose each of these. Here we have our Legos on the right. Can you identify those? We have plagioclase in the white feldspar. We have this pinkish microcline or potassium feldspar. Beneath that, we have quartz. And then over to the left, we have hornblende and biotite, and then muscovite mica down at the bottom right. If we put that set of Legos together and we cool them underneath the surface, we form granites. And I've included a photomicrograph from a petrographic microscope, a polarizing light microscope, to show you the world that geologists see when we look at thin sections of these rocks under our microscopes. And we can tell all kinds of things about their chemistry simply from looking at them under the microscope and identifying those minerals. If we have that same group of Legos, we're going and have them in a fast cooling environment in a volcano, we're going to produce something else that we'll see in a moment. But we're going to stay here with the plutonic rocks, those under the ground. If we take our Legos and get rid of the quartz, we get rid of the really alkaline-rich feldspars, the sodium and potassium-rich feldspars, and we go with this assemblage. We have our plagioclase at the top. We have hornblende in the middle. And we have biotite mica, the iron-rich mica at the bottom. We produce diorites. These are the kinds of things we usually find inside of those big cone-shaped volcanoes. See, the granites are going to be way far down. The diorites are going to be a little bit higher up in those volcanoes like Mount St. Helens, Mount Rainier out in Washington. The photomicrograph shows you a nice zebra striping of the plagioclase feldspars. This is something called polysynthetic twinning. That's a fancy name, I know, but this is one of the, again, I like sharing with you this world that we see under the microscope. And finally, at the very mafic end, we have gabbros. Those are composed of our Legos, augite, pyroxene, and calcium-rich plagioclase, trending toward that anorthite end member. We see those there in the polarized light image through the microscope. The very brilliant colors, the rainbow colors, are the pyroxenes. The zebra-striped ones are the feldspars. When we have about 50% of each of those, we have a gabbro, or a basaltic composition. But remember, basalts are going to form in our volcanoes, out cooling fast. Gabbros are cooling underneath the surface. So this would be what you would expect to find if a magma chamber in Hawaii cooled underground. And then finally, we have some rocks that are called ultramafic, super magnesium and iron rich. And those often we see as dunites or periddotites. You may be familiar with the term peridote, the gem variety of the mineral olivine. Very pretty green, like you see in some of the rocks I'm showing here. But when we have these rocks that are composed mainly of olivine and pyroxene, maybe with a little bit of calcium plagioclase, we have these dunites and periddotites. These typically are what you find in the upper mantle of the earth, and we often see them as xenoliths. That's foreign rocks that are picked up by magmas coming out, and they're brought out from deep underneath the crust. But they're, as you see, coarse-grained when they're down deep like that, because they cooled at great depth very slowly. But when we talk about those extrusions, those volcanic rocks, now we talk about some different things. Here we have the same building blocks as a granite. We have the microcline or potassium feldspars. That same type of feldspar can occur in different crystallographic forms that we call orthoclase and sanidine. Sanidine typically is a very high temperature feldspar, so it's really what you'd find in many of these explosive volcanic rocks. But you put those potassium feldspars together with quartz, together with micas, and you form rhyolites. They tend to be very light colored rocks. They don't have much iron in them. And here you see a photomicrograph, two photomicrographs that also show you, they see these really dark areas in the image. Those are bits of glass. So these are places where we have volcanic extrusions where some of the magma is cooling so fast that it creates a glass as part of that rock. Andesites are intermediate lavas. They're the extrusive equivalent of the diorite. So do you remember what Lego blocks they're made of? They're made of primarily amphiboles, hornblende. In the rock here, you see these little black, they look like little black blocks. In the photomicrograph, you see the sort of brownish crystals. Those are the hornblendes. And then we have plagioclase, sort of intermediate calcium-sodium plagioclase. If you put those together with hornblende, you get diorites if they cool under the ground. If they come out of the volcano, they produce andesites. You'll also notice that andesites typically are those porphyritic rocks. Why would that be? Remember what porphyritic means? It means that you have a fine-grained ground mass or matrix, like the soft part of your chocolate chip cookie, and then you have in that the phenocryst, the crystals that are like your chocolate chips. So this happens because, well, andesites are volcanic, right? So they're cooling underground and then suddenly erupt out. So those hornblende phenocryst are cooling slowly in the magma down before it erupts. Then suddenly it erupts and the rest of the magma cools very, very fast to form that fine-grained texture that you see. Andesites we commonly associate with those big stratocombs. Remember I said the diorites would be inside the volcano, but the andesites would come out. So many of the lava flows that we see coming out of a place like this is the San Francisco Peaks volcano in Flagstaff, Arizona, we would see those andesitic lava flows coming out of that. In fact, we do. And then finally, basalts. Basalts, they are the fine-grained equivalent of those gabbros. They're made primarily of pyroxenes, particularly augite, and plagioclase, typically more calcium-rich plagioclase. You put those together, about 50-50, you cool them really fast, and you produce basalts like we see here erupting there in the lava flows of Hawaii. That steam there at the back is literally steam coming out of the ocean where the lava flows are going out into the ocean and heating up the water very quickly. We also have basalt flows I want to show you here that are part of Great Flood basalts. This is in the Columbia River Plateau right at the border of Washington and Oregon, very close to where they meet Idaho. These are part of the Columbia River flood basalts, and you see these very, very thick flows that are now covered with grass. And then finally, we have those special categories of igneous rocks, those that cool really, really, really fast. But they form glass. And pretty much everybody is familiar with obsidian, right? Obsidian looks very dark, but here's a secret. It's not. If you break off little tiny bits of obsidian, the bits that you break off are as clear as plate glass. That's because its composition is not iron-rich. It is the really, really fast cooling equivalent of granites and rhyolites. It's a rhyolite that cooled so fast that the crystals couldn't form. Sometimes you'll hear people talk about obsidian being any volcanic glass, and that's not how igneous petrologists use the term. Mafic glasses typically do not form anything that looks like obsidian. Obsidians typically are part of those big silicic volcanoes, often part of those big sticky domes, like I showed you, that come out and move very, very slowly. On the mafic end, the iron and magnesium-rich end, we have things like you see here with Pele's hair, and this sort of spongy stuff called reticulite. These are the volcanic glasses that you would find in Hawaii, where the basaltic magma cooled so fast. It erupted out, was thrown up in the air, cooled super fast, and solidified to glass rather than forming minerals. And then we have those gas-rich vesicular rocks. On the felsic silicic end, that one with the quartz and the potassium feldspar, we have pumices. So if we have a lot of gas in that rhyolitic or granitic magma and it's bubbling, that gas can escape as the eruption is happening, and we form these blocks of pumice that are very light colored, pinks and tans. On the mafic end, we have scorias. Scorias are often, basically, we could call them scoriaceous basalts, but these are like your lava rock that you find in the landscaping material. A lot of the lava rock, the scoria that we have around the United States, comes from the mining of a couple of cinder cones out in the area around Flagstaff. And so the area around Flagstaff has every sort of volcanic rock, all the way from that big high peak of andesite that I showed you with the San Francisco peaks to basaltic lava flows and cinder cones nearby. All right, so that concludes our presentation of igneous rocks today. I apologize that we weren't able to have it fully dynamic with me on the camera and everything, but hopefully this will be useful for you to show to your students and as a review of those igneous rocks that are out there. If you do have any questions, please feel free to email me at scott.harris@fernbank.edu. Hopefully I'll see you next time at 1 o'clock on next Tuesday for our next installment of Fernbank Rocks with sedimentary rocks. Thank you very much.